Hey everyone, this video is an introduction to multidimensional IRT models. And I say slash Roche models because most of these that we would be looking at would be a one parameter, which is conceptually and mathematically the same as Roche model. Do pause and look at this comic because this is where we are going. What is so freaking cool about multidimensional IRT models is that it's a combination of IRT, so the Roche type stuff that we've been looking at, and factor analysis. So we get all of the really cool IRT stats that we've been looking at with the Roche model, but we also get the factor analysis aspects where we have fit statistics and trying to kind of figure out, is it unidimensional, two-dimensional, four-dimensional, 6 dimensions? How many dimensions do we have within this construct that we are understanding? So it's a combination of the two. So this is directly from Briggs and Wilson, that you should definitely check out their article from 2003. It's posted in Canvas. If you don't have me, check it out. And it's modeling science ability. And this figure really solidified everything for me. So we have this bottom part that's sort of like a CFA where we're trying to see, do these items load on these intended factors that we are predicting that they should. But you'll notice that the arrows are flipped. And so here we're actually using these factors as predictors. Do these items predict this latent concept? And on the backside of those same items, these are our individual models. So these would be like the Roche models that we have been doing. They are individual, one parameter or two, depending on what you're doing, I guess. But this is the latent trait that we are modeling on the backside. Even cooler is that all of these Roche models, compared to what we've been talking about, all of these IRT models get to interact with each other. And so dimensionality might actually relate to another dimension on another Roche model. This is especially true when we see situations where you have one dominant factor and then some kind of sub-factors that, is it unidimensional? Is it 4 dimensions? It could be one, it could be both. That's how all of this gets to work together. And so here when we talk about latent ability, we're talking about the probability of a response in any of the 4 categories based on the last picture. And so it would be a function of a student's latent ability of science ability as a whole. And so what they're doing is they're modeling science ability based on 4 different factors. And what this model does is it shows the student's latent ability as a whole, and we would get 4 person abilities because they interact with each other across all of the items. This gets a little bit confusing because we actually have all of the items together in a single ruler, but the 4 factors allow the person to vary across each factor. So person ability gets to vary based on the 4 factors. Here's what that looks like with a 2-factor model. So this is exactly what we see with our right map, our item person map. We've got our items scaled across here from 1 to about -1.5 in this case. And then we have 2 latent traits, so 2 factors, and the persons get to vary based on those abilities, based on those factors. So we can see that in dimension 1, in factor 1, we have a lot lower ability than we do in factor 2. So this sample has more ability in factor 2 than it does in factor 1. Here's another, blurry example, but we have our items and then we have 4 different traits, and we can see that this 4th dimension, this 4th factor, we have a lot more ability compared to dimensions 2 and 3. Here's another example with 5 dimensions. So not only do we see these items are all mapped out, but we can see that person ability varies quite a bit between these 5 factors. Specifically, again, turn your head so that you can see what I'm going. We have dimension 1, so factor 1 is really tight. Everybody's grouped really closely together and there's not a lot of spread compared to factor 2 and 3 where there is a ton of spread throughout these abilities. So the mean scores of these tend to be, or are in this case, pretty similar, but the spread is quite a bit different based on ability. This is a little bit different than what we looked at with WinSteps table 1.4, where items are actually changing, sort of. So here we would have our persons, and this middle column is our items. If we just deleted these kind of other two columns, this would be table 1.1 and 1.2 that we've been looking at. But what this table adds on is the bottom 50% and where items would match them. And then it takes the top 50% and where items would match that group. So it just shows where items are spread a little bit differently by person. So coming back to mIRT, we do have model fit because we are comparing and trying to figure out factors. So we have to have some sort of a model fit to see, is unidimensional better, two-dimensional better, four-dimensional better, all kinds of things. And if you're using our software specifically, we're looking at statistic called M2. This is conceptually really similar to a chi-square. In fact, we interpret it like a chi-square. You'll also have RMSEA and CFI. If you have no idea what I'm talking about because you haven't taken SEM, that's fine. Just know that there are different fit statistics that you're going to be comparing to try to figure out which one you like the best. We also, especially if you've had SEM with me, when we looked at different models, we compared fit, especially when we were looking at group differences. We actually looked at change in statistics. So we looked at change in chi-square, change in AIC. Here we're looking at change in G2, it's just another statistic, and change in AIC. So we literally are taking model 1 statistic minus model 2 statistic and seeing if the p-value is significant for that delta, that change between those two. If it is significant, then that means that the models are significantly different, and then you have to kind of figure out which one is you consider better than the other one. So it's a little bit more than just getting models to run with mIRT, although that is the first step. You definitely need a lot larger sample size than some of the Roche models that we've been doing. And then you get to decide what is best. And so the first step is really those model comparisons. Which model is the better choice that kind of fits the data and fits what you think conceptually. And then you get to examine all the cool IRT tables that we look at. And of course, none of this is quite as straightforward as we'd like it to be because there's decisions that we're making. And so this is a little bit different than Roche model, where the Roche model is unidimensional, and if it's not, it doesn't fit. And the model trumps everything. Here, we're saying the data influences the model, but the model is still the model. And so you have conceptualized this model, you have put these parameters together, and you're seeing, does the data fit that or not fit that? Once you have the comparison and you decide which one you think is best, then you get to kind of get all of the benefit of the IRT stuff that we've been looking at.